Hello students, in this lecture we are going to study the biogenesis of nicotine in which pyridine ring is present. So this is the structure of pyridine ring. So nicotinic acid, how it is synthesized, we are going to see. So precursor for this, it is tryptophan. So in presence of tryptophan, pyrrolase enzyme and iron and O2 dioxygen, so it forms the N-formyl kynurenine. So what happens here? So this double bond, it breaks and it forms the two carbonyl groups. So this is the, after that hydrolysis it gives the anthranilic acid. So what is the mechanism? So this is the indole ring having, after breaking we will get two carbonyl groups here. So in presence of kynurenine formylase enzyme, it gives the hydrolysis of this bond, so we will get NH2 here. Then again hydrolysis of this bond and O2 NADPH is gives the introduction of OH at this position. This is the 3-hydroxyl anthranic acid, it is formed. So 3-hydroxyanthanilic acid in presence of dioxygenase enzyme, it gives the rupture of this bond and we will get the two carbonyl groups. These are the two carbonyl groups. So these two carbonyl groups are formed. After that there is a cis trans isomerization of double bond, this double bond, so it is reversed, so we will get NH2 and CHO at closer. So this NH2, it having lone pair, nitrogen having lone pair, it reacts with this carbonyl group and we will get the pyridine ring. This is the quinolinic acid. So quinolinic acid, with when it there is a decarboxylation reaction here, minus CO2, it gives the nicotinic acid. So acetic acid with Krebs cycle, it forms the succinic acid and again oxidation, it gives the oxaloacetic acid. So this oxaloacetic acid with transamination reaction, it gives the aspartic acid. So this aspartic acid, when it reacts with the 3-glyceraldehyde 3-phosphate, it will form a ring, 6-membered ring having nitrogen atom. This nitrogen ring with dehydrogenation reaction, it gives the quinolinic acid and after decarboxylation it gives the nicotinic acid. So how this nicotinic acid is formed, we have seen. So next it is biogenesis of pyrrolidine ring. So in nicotine alkaloid, so we are going to study the biogenesis of nicotine alkaloid. In this there is a nicotine ring and pyrrolidine ring. So nicotine ring synthesis we have seen. Now pyrrolidine ring structure. So in this, precursor for pyrrolidine ring is ornithine TC14, ornithine and labeled 2C14. Ornithine decarboxylase, in presence of this enzyme, it gives the decarboxylination reaction. So minus CO2, it will give two NH2 groups here. So this putrescine compound, in presence of SAM and putrescine N-methyl transferase enzyme, it gives the methylation of this NH2 group, that is NHMe is formed. Again transamination of this compound, it gives the exchange of NH2 with C double bond OH group. After that this N4N-methyl amino butanol, it nitrogen having lone pair electron, it reacts with this carbonyl group and we will get the 5-membered ring, it is called N-methyl pyrrolinium ion. So we have seen the biogenesis of nicotinic acid and N-methyl pyrrolinium. So how the joining of these two rings may be, let's see. So this nicotinic acid in presence of NADH, what happens? Hydrogens are provided and this reduction of this double bond takes place here. So nitrogen lone pair it interacts with this pyrrolinium ion and it forms the bond between two rings. Again, it gives the aromaticity of this ring is maintained. So this is the formation of nicotine alkaloid. Now biosynthesis of piperidine ring of anabasine. So precursor for this is lysine. So lysine, in presence of PLP, it gives the decarboxylation reaction. So it will form the codaverine. So pyrrolidine alkaloid we have seen from the precursor ornithine C14, how it is that N-methyl pyrrolinium ion is formed, we have seen. So first decarboxylation, then N-methylation, then transamination reaction, and then intramolecular Schiff base. It gives the pyrrolinium ion. We have seen just now how this pyrrolinium ion is formed. So again, this pyrrolinium ion, when it reacts with the enolate of acetyl coenzyme A, so we will get this enolate. It will react with the superposition of this N-methyl pyrrolinium ion. We will get this compound. So this is the intermediate after removal of this coenzyme ASH. It gives the high green, and then minus coenzyme ASH and minus CO2, it gives cuscohygrine. And when this intermediate reacts with this N-methyl pyrrolinium ion, we will get the cuscohygrine. And when this intermediate with minus 2 hydrogens, it will give the N-methyl pyrrolinium ion, and intramolecular managed reaction, it gives the this compound, and the name of this compound it is tropinone. This is the tropinone. So hydroxylation of this tropinone, this is the OH, and compound it is called tropine. Then this is the cocaine and hyoscyamin. So these are the pyrrolidine alkaloids with precursor ornithine C14. So piperidine alkaloids. Then piperidine alkaloids, we have seen the precursor, it is lysine. This is the lysine. So we know that the pyrrolinium, N-methyl pyrrolinium synthesis we have seen, and that the steps are same. Similar steps are here for N-methyl piperidine ring. So first it is decarboxylation, then N-methylation, then transamination reaction, then intramolecular Schiff base formation reaction. So this will give a intermediate N-methyl piperidine ring. And when it reacts with the malonyl coenzyme A enolate, so we will get this intermediate. When this intermediate after decarboxylation and minus coenzyme ASH, so it will give N-methyl isopelytrine similar to hygrine. So this is again a alkaloid with precursor lysine. And when this is NH, it is pelytrine. So N-methyl isopelytrine with minus 2 hydrogen, so it will give, so minus 2 hydrogen, it will give the oxidation reaction, and it forms the double bond over here. And intramolecular managed reaction, it will give pseudopelletrine. This is the pseudopelletrine. So this is the anaferine analogues to cuscohygrine alkaloid. And the precursor for this, it is L-lysine. So quinolizidine alkaloid, also called as an lupine alkaloid. So this is the basic structure. So the precursor for this, it is L-lysine. The structure we know, L-lysine, how it is converted to this codaverine by decarboxylation using pyridoxal phosphate, PLP. So after that, there is a transamination reaction. One of the NH2 is exchanged by carbonyl group. Then intramolecular She-base reaction, it gives the 6-membered ring having nitrogen atoms. So this is the intermediate. So when these two intermediates, enamine and imine, when it reacts with each other, so it will form a bond at this position. So how it is formed? So this nitrogen, this lone pair are reacted with this the second molecule of second imine carbon atom. So this is the reaction. So after that, so again a hydrolysis, it gives the rupture of this bond, NH2 here and CHO here. So this is the similar structure, and after transamination reaction, so this NH2 group, it is converted to or exchanged to carbonyl group. So She-base reaction of this nitrogen and carbonyl group, aldehyde group, it will form the She-base reaction. So this is the She-base reaction. It will form the joining of two rings in presence of NADH. It gives the reduction of this double bond. It provides the hydrogens. Also, this CHO group, it is reduced to CH2OH. So this is the compound lupinin alkaloid.